Okay, welcome to lecture 3, Friday of week 1. Today we'll talk about span and linear independence, or as much as we can in the next hour or so, which is section 2.a in your textbook. Okay, so let me just remind you of some definitions. First definition is the definition of a linear combination. Right? So a linear combination is just a way to take vectors and to produce a new vector, right? By combining them linearly, which means scalar multiplying and adding. And so here's the definition. A linear combination of some vectors, say v1 through vm in V, is a new vector of the form a1 v1 up through am vm, where each of these AIs is a scalar in F. Okay? So you have some collection of vectors. To take a linear combination just means you scale them by different scalars potentially, and then you add them up. Okay, and then we have a special word for the set of all linear combinations of a set of vectors, and that's the span. So the set of all possible linear combinations of some vectors v1 up through vm and V is called the span of v1 up through vm, and is denoted in your textbook and in the notes, span parentheses v1 up through vm. Okay, so this thing here denotes a whole collection of vectors, every possible linear combination of the vectors v1 up through vm. So to be very explicit, this is a set of vectors. This is a set of all possible linear combinations. So a1 v1 up through am vm, such that a1 through am are scalars in F. Okay, and then just by convention, this is just an edge case, but we say that the span of the empty list or the empty set is just the vector that contains, the set that contains just the zero vector. Okay, so we only say this so that every span will be a subspace. We'll see that in a second. If we didn't cover this edge case, then the empty set is not a subspace. So this is just a technical detail. Okay, so let's look at some examples before we prove anything, right? So we should always start by visualizing things that we are comfortable with. So if V is a vector in R2, well, we can take the span of a single vector. What is that? That's all possible linear combinations of just this vector V. So that just means all scalar multiples of the vector V. Right, so if V is a non-zero vector, then what is this whole set of vectors? Well, it contains V, it contains 2V, it contains 3V, it contains 1/2 V, negative V. So the span of a non-zero vector in R2 is just this entire blue line through the origin. Right, this is if V is non-zero. Okay, because of course, if V is the zero vector, you can definitely take the span, but then all possible linear combinations is all possible scalar multiples, in which case you just get the zero vector. Right, so this is span of the zero vector. Okay, next example that we can picture. Let's now suppose that you have two vectors, v and w in R3. Right, because again, this is maybe now the highest dimension that I can picture anyway. So we can picture this as the xy plane is living in the plane of the screen, and the z-axis is coming out. Right, and then you take two vectors. Maybe I'll use a different color here. V and w. Well, what are all the possible linear combinations of v and w? Well, you can certainly scale v by any vector that you want, right? So you get this entire line. You can scale w by any vector that you want. That's a linear combination. So you get this line, but then you also get all possible linear combinations. That means you can add any scalar multiple of v to any scalar multiple of w, right? So you'll get like this vector. This vector is v plus w. And in the end, what you get is you get this entire plane through the origin, right? So this is the span of v and w in R3. But in the way that I've drawn this picture here, I've made sure that they're both non-zero vectors and they're both not scalar multiples of one another, right? So this is if v, w are non-zero and not scalar multiples. This is sort of like the generic case, right? Of course, if they were both a zero vector, you would only get 0 if you take linear combinations of the zero vector. Or in R3, again, if they happen to be scalar multiples of each other, right? So if this was v and w was like, I don't know, negative 1/2 v, as you added scalar multiples of this to scalar multiples of this, you would never leave this line. So the span here, this is the span of v and w if v were equal to lambda w and at least v is non-zero. Okay, so you get a whole set of vectors. What the set of vectors looks like, at least when you can picture it in Rn, is it looks like some flat thing through the origin. Okay, and it turns out that the span is always a subspace. And it even has like a further property, which is the content of this next result. So the set span, parentheses, v1 up through vm, is the smallest subset, the smallest subspace of v containing v1 up through vm. Again, this proposition is stating two things. It's stating, first of all, that the span is a subspace. So that's one claim that we need to prove. We need to prove that it actually is a subspace. But then the second claim is that, well, you can think of this almost as three claims, but the second claim is that the subspace contains the vectors v1 through vm, and it's actually the smallest subspace containing it. Okay, so there's several things that we need to prove here in order to prove this proposition. So first, let's show that this span is a subspace. Okay, so just for notational ease, let's call this thing S, right? The span is S. S is all possible linear combinations of v1 through vm. So first, let's show that S is a subspace. Okay, well, how do you show that something is a subspace? You show that it satisfies the three criteria of being a subspace, which we covered, I'm already forgetting. Was it last lecture? Yeah, right? So this proposition from last lecture says you're a subspace if you contain 0, you're closed under addition, you're closed under scalar multiplication, right? So does S contain 0, right? It does, because that's just asking, is 0 a linear combination of v1 through vm? Which it is, because you could take all the scalars to be 0, right? So note that 0 is 0 v1 plus 0 v2 up through 0 vm. So this means that 0 is a linear combination, which means that 0 is in the span, which means that 0 is an S. So that's one thing we need to check. We now need to check that S is closed under addition, right? So let's suppose that U and W are both vectors in S. I want to show that U plus W is in S. Well, what does it mean to be an S? To be an S means that you are a linear combination of v1 through vm. So since U and W are in S, what does it mean? This means there exists scalars. It can be A1 through AM and B1 through BM, such that U is A1, B1 up through AM, BM, and W is B1, B1 up through BM, BM. This is just what it means to say that u and w are in S. I'm interested now in their sum, so I should add them together. But then you can group by which v they're associated to. A1 plus B1 B1 plus AM plus BM BM, which again shows that u plus w is a linear combination of V1 through Vm, which means that u plus w is in the span of V1 through Vm. In other words, u plus w is in fact in S. Okay, so then we need to check that's close under scale multiplication. You should do this, but what you do is you take this vector u, right? You take this vector u, and you take any scalar, maybe alpha. You need to show that alpha u is an S. Well, what do? You just scalar multiply by alpha. That's the same thing as multiplying all of these a1 up through am by alpha. And then, well, alpha times a1 is a scalar. Alpha times a2 is a scalar. Alpha times am is a scalar. So the resulting vector will still be a linear combination of v1 through vm. The resulting vector will still be an S. Okay, so you should write it up. Check that if u is an S and alpha is a scalar in F, this implies that alpha u is also an S. Okay, so these three things together, right? Maybe I'll label them like this. So by the proposition from last time, if you have 1, 2, and 3, this implies that S is a subspace. So the span is always a subspace. Okay, now I need to show that it's the smallest subspace containing V1 through Vm. Right, so how do you prove that something is the smallest subspace containing V1 through Vm? First, I need to show that it contains V1 through Vm. Then I need to show that any subspace which contains V1 through Vm contains S. Okay, so let me just write down this outline. So for the second claim, what should we do? We should first, A, show that V1 through Vm are in S, right? Because if you're going to be the smallest subspace containing them, you better contain them. B, we'll show that if T is any other subspace which contains these things, that actually T already contains S, right? Any other subspace containing them is bigger than S, which means that S is the smallest one. Okay, so how can we prove that V1 through Vm are in S? We need to show that V1 through Vm are linear combinations of V1 through Vm, right? But this is clear. So for A, for each Vi, we have Vi equals 0 V1 plus 0 V2 plus 1 times Vi, whatever the Vi is, plus 0 Vm, right? You just take the scalar for the Vi to be 1, all the rest of the scalars to be 0. This shows that Vi is an S for all I. So that shows that S contains V1 through Vm. Now I want to show that it's actually the smallest thing. So for B, suppose T is a subspace containing V1 through Vm. Well, since T is a subspace, that means that T is closed under addition and scalar multiplication, right? Since T is a subspace, it is closed under addition and scalar multiplication. Which actually means that it's closed under taking linear combinations, right? Because if you have any linear combination, let's look back up here where I've written down a linear combination again here up at U. If you take any linear combination of these vectors, it's just you've scaled all the vectors and you add them together. Well, since T is closed under scalar multiplication, it contains all of these scalar multiples. Since it's closed under addition, it contains their sum. That means that T is closed under linear combinations. Under taking linear combinations. Which means that since it contains V1 through Vm, and it's closed under taking linear combinations, it means it contains every possible linear combination of V1 up through Vm, which just means that T contains the span of V1 up through Vm. So T contains all linear combinations of V1 up through Vm. And this means that T contains the span. Okay, so let me just mention, when you are writing mathematics, for example, in your homework assignments, you should write in complete sentences, as we learned in Math 300. And you should also include all the details, including some of the ones that I'm saying verbally, should be written out. Right? So in a lecture format at the board, you can explain a lot of things in words without writing down every single word. But when you write an argument down on paper, you should make sure that whoever is reading it can understand your proof. So my proofs will be a little bit more shorthandy and a little bit less word in the write-up than you should strive for on your homework. Okay? Of course, on tests where there's a time limit, right, it's okay to use some shorthand, to not use complete sentences, as long as you're very clearly making your point. And you maybe don't need to give so much detail when you're under time pressure, but for your homework assignments, you should really strive to make it so that in 1 year, when you look back at your homework assignments, because you are trying to remember something learned in your algebra, and you read, that you will be able to understand in 1 year, even after you've forgotten a bunch of stuff. Okay. So that's the definition of span and the proof that the span of a set of vectors is a subspace. Let me just make another definition related to span. So if the span of some vectors v1 up through vm is actually equal to v, then we say that this set of vectors v1 up through vm spans v. Okay, so note the difference between these two definitions, right? Here I define span. The span of a set of vectors, that's a noun, right? The span of a set of vectors, that's a whole collection of vectors. What is this definition? Here I'm defining the verb to span. If I say that a set of vectors spans V, what I mean is that their span is actually equal to all of V. In other words, every vector in V can be written as a linear combination of these vectors. If that's the case, then the span of the vectors is equal to V, and you say that the vectors span V as a verb. Okay, so just an example. Maybe the most intuitive example is consider the vectors, and this is standard notation. So E1 will be the vector. This is like the first standard basis vector. E2 is the second standard basis vector. Up through En is the nth standard basis vector. These are all in Fn. Right, so you can look at the span of these guys. That's what all possible linear combinations of these n vectors. But then it's pretty clear that you can get every vector in Fn, right? E.g., I mean, this is just, if you want to get the vector, I don't know, pi -1, 0, you can just take pi of E1 minus E2 plus 0 E3. Right, so no matter which vector you want to get, you can pick the coefficients on your standard basis vectors such that you can get that vector. So the span of these vectors is equal to all of Fn. Right, that's the span of these vectors. Or you could say that E1 through En, that this set spans F to the n. Right, so these are the two statements that you can make using the word span. One as a noun, one as a verb. Okay. But of course, as we learned at some point in the quarter, it's only been a week, I'm forgetting which day we did what, f to the n is not the only vector space, and it's not the only one that we should use in examples to try to understand the concepts, right? Because we want to be able to apply them more generally. So now I'll formally make the definition of polynomials, and I'm going to switch notation from what I did in lecture 1 to agree with what your book has. When I was doing lecture 1, I hadn't read this far in the book yet. I didn't realize that there was a notation that Axler prefers. So from now on, we'll use the following notation. Okay, so let sort of a script pf denote the set of all polynomials in one variable z with coefficients in f. Okay, so last time, or maybe 2 times ago, I used the notation rz for all the polynomials with coefficients in R. This is actually kind of more standard in mathematics, but since I don't want to be confusing between what I say on homework or in the notes and what the book says, we're going to stick with this book notation. Okay, so in other words, PF, this is all polynomials. So it's all elements that look like A0 plus A1z plus AN z to the n, where A0 through AN are scalars and n is some natural number. Right? So everything that, all the polynomials that you can make with the variable z with coefficients in f. Okay, and then some more maybe definition or notation. So if m is a non-negative integer, so if m is an n, we'll put a little subscript of an m here, Pm of f, denote the subset of Pf consisting of polynomials of degree at most m. Okay, so like P3 of f contains all the cubic, quadratic, linear, and constant polynomials, but not z to the 4th. Okay, and you should check for yourself. I keep on clicking things that I don't want to. Check that Pm of f is a subspace of P of f, right? I mean, we can do it in words right now. 0, the 0 polynomial, that's a polynomial of degree, I guess, either 0 or negative infinity, depending on the convention. But certainly it's a polynomial of degree at most m, right? If m is a non-negative integer. So the 0 polynomial is definitely in Pm of f. Also, if you add 2 polynomials of degree less than or equal to m, then you get a polynomial of degree less than or equal to m, right? Adding polynomials does not up the degree. It could down the degree, right? X squared minus x squared, or z squared minus z squared is 0, so the degree went down, but you never increase the degree. And if you scalar multiply a polynomial of degree less than or equal to m, you again get a polynomial of degree less than or equal to m. It's either the same degree, or if you multiply it by 0, then you get the 0 polynomial. So it's closed under addition, scalar multiplication, and contains 0. Okay, so now that we have this standard notation for this set of polynomials and the set of polynomials of degree at most m, we can talk about some spanning sets. So the monomials 1, z squared, z cubed, ... These span the vector space of set of all polynomials. Right? Why is this true? Well, again, what is the span of these polynomials? It's all possible linear combinations of those polynomials, and of these monomials. And we know that every polynomial you can write as some linear combination of these monomials, right? That's sort of the definition of a polynomial. So these infinitely many monomials span P of F. On the other hand, the monomials 1z, z squared, up through z to the m span Pm of F. Right? If you want to get a polynomial of degree at most m, it suffices to take linear combinations of just these m+1 monomials. Okay. More definitions. We say that a vector space is finite dimensional if it is spanned by finitely many vectors. Right? In other words, there's a finite list of vectors such that every vector in the vector space can be written as a linear combination of that set. Okay, so otherwise, we say that the vector space is infinite dimensional. Okay, so this now has a very precise mathematical definition. If there is a finite list of vectors that spans it, it's finite dimensional. If not, it's infinite dimensional. Okay, so e.g., P of F, the set of all possible polynomials, this is infinite dimensional. Right? Let me just give you the verbal argument as to how you can show it's infinite dimensional. To say that it's infinite dimensional means that you cannot write it as the span of finitely many vectors, or in this vector space, the span of finitely many polynomials. Okay, so suppose you had finitely many polynomials that spanned, right? So here's the proof, just the proof sketch. Right, if you suppose, I mean, if you take the span of finitely many polynomials, maybe f1 up through fn, I want to show that you can't possibly get all of the polynomials. Well, you can look at each of these degrees, right? So suppose that this one has degree d1, this one has degree d2, this one has degree dn, right? Whatever the polynomials are, you can look at the highest non-zero term that gives a degree. And then you just look at the biggest degree here. There's no way to get a polynomial of degree bigger than that by taking linear combinations, because taking linear combinations can never up your degree, right? Then you take the max, you let d be the max of these degrees, d1 up through dn. Then the span contains no polynomials of degree capital D plus 1, which shows that these vectors, these polynomials, don't span all the polynomials because you're missing at least some of them. Okay, so this vector space is infinite dimensional by that little argument. Pm of F, this one is finite dimensional because we already wrote down a spanning set, 1z, z squared up through z to the m. Okay, also similarly, kind of similarly, this vector space f to the infinity, right? All infinitely long lists of elements from f. This is infinite dimensional. On the other hand, f to the n is finite dimensional because we already saw that the n standard basis vectors span f to the n. Okay, so let me just remind you of your intuition from Math 308 behind spanning, and then also behind linear independence. So just remember, what's the intuition? We now have like the precise definition, but the intuition should be that spanning V, this kind of means like points in every direction in V, right? Because it means that you can get everywhere in V just by taking linear combinations of the vectors. Right? So again, if you picture R3 like this, and there's basically 3 directions in R3, right? So like if you took 2 vectors in R3, we said in general the span should be like some kind of plane. So these 2 vectors are not going to span R3 because you can't get everywhere in R3, right? They're not pointing in every direction because they're not pointing out of the plane, right? But once you add another vector which points out of the plane, right? In this picture, what I've drawn anyway, now you can get anywhere along the plane, and then you can take some scalar multiple of this green vector to sort of lift out of the plane, and you can get everywhere in R3. These 3 vectors sort of point in all of the directions of R3. Okay, and you can even add another vector, right? And now these 4 vectors will still span R3 because the first 3 already spanned R3. So here you're just adding sort of more freedom, but you actually didn't need it. You can still get everywhere in R3. So the idea behind spanning should be something like your vectors point in every possible direction. By which I really mean you can get everywhere by taking linear combinations. Okay, so that's the intuition for spanning V. But now you maybe also remember some notion of linear independence. So the notion of linearly independent somehow means pointing in different directions. Right, so the intuition for a linearly independent set, which we'll define in 1 second, should be vectors that point in different enough directions. Okay, so like these first 2 red vectors that I've drawn, those are linearly independent because they're pointing in different directions. But if you took a scalar multiple, if you took the first red vector and the scalar multiple red vector, those 2 are not linearly independent because they point in the same direction. But we'll see, I'll recall what the definition is. I just want to remind you of your intuition for when you're thinking about these things. It often helps to have some sort of picture in your head. Okay, another bit of intuition, the way that I would state it in 308 is, another way to say linearly independent is maybe not redundant. Somehow you need every vector, right? Because they're pointing in different directions. If you took away one of the vectors, you would lose something. That's what it means to be linearly independent. Okay, of course, that's not the definition. That's just the intuition. What's the definition? I'm glad you asked. Definition. So a subset of vectors, maybe V1 through Vm, in a vector space V, is called linearly independent if the following condition holds. If you have a linear combination, in my notes I've used the letter N here. I don't know why I switched, but let me be consistent with my notes, I guess. If you have a linear combination which equals 0, then it must be the case that all of your scalars were 0. So if this implies that A1 equals A2 equals AM equals 0. Okay, so to be linearly independent means that the only linear combination which equals 0 is the trivial linear combination. There's no way to write 0 non-trivially as a linear combination. Okay. By convention, again, just for edge cases, the empty set is linearly independent. Okay, otherwise, we say that the set V1 through Vn is linearly dependent. Okay, well, what does that mean? That means that it fails to be linearly independent. It means that the statement that the only linear combination which equals 0 is the trivial linear combination is false. So another way to say linearly dependent is to say that some non-trivial linear combination of the vectors equals the 0 vector. And so another way to say this is that there exist scalars a1 through an, sorry, this should be an n too, in F, not all 0, such that a1 b1 plus an bn equals 0. Okay, so somehow the statement of being linearly dependent is like an existence statement. It's a bit more constructive in a way. Say set of vectors is linearly dependent means that there exists a set of scalars. The definition of being linearly independent is sort of a universal statement. It's saying no matter what you do, you can never get 0 except for the trivial linear combination. Okay, so we will of course prove some results about linear independence, but let me just start with some examples. Okay, so what if you have a single vector v? Okay, well, to be linearly independent should mean that the only linear combination which equals 0 is the trivial linear combination. When you're taking a single vector, when you take linear combinations, it just means scalar multiples. So to be linearly independent should mean that the only scalar multiple of this vector which equals 0 is 0 times v, which is the same thing as saying that v is non-zero. Okay, so this singleton set is linearly independent if and only if v is non-zero. So if v is 0, right, this set is linearly dependent because, for example, I don't know, 2 times the 0 vector is 0. That's a non-trivial linear combination which equals 0. Okay. Second example, let's say you take 2 vectors in V. Okay, so this is linearly independent. You can probably show this by hand. If and only if V is not any scalar multiple of W, and W is not any scalar multiple of V for all lambda. Right, so as long as the 2 vectors are not scalar multiples of one another, then the vectors will be linearly independent. Okay, note that if one of the vectors is 0, then it's already a scalar multiple of the other one. So if you contain the 0 vector, you will automatically be linearly dependent because there's a non-trivial linear combination which equals 0. Okay, so this, I mean, I haven't stated it quite explicitly, but this condition includes the fact that the vectors must be non-zero, otherwise they would fail the condition. Okay, our other familiar example, 1z, z squared, z cubed. This is a linearly independent subset of polynomials of P of f, or even Pm of f for m bigger than or equal to 3, right? Otherwise, if it's not bigger than or equal to 3, it won't contain z cubed. Okay, so how can we argue that this set of polynomials is a linearly independent set? Well, we need to show that the only possible linear combination which equals 0 is the trivial linear combination. Right, so if you suppose that a naught plus a1z plus a2z squared plus a3z cubed equals 0, right? So suppose you have a linear combination which equals 0. Well, what is the 0 vector in the set of polynomials? It's the constant polynomial 0, right? So what this says is that this polynomial is the constant polynomial 0. But a cubic polynomial, maybe I should say a non-zero cubic polynomial, has at most 3 roots counted with multiplicity. Right? We all know this fact. It's called the fundamental theorem of arithmetic. Fundamental theorem of algebra, that a degree n polynomial has at most n roots, but the 0 polynomial has infinitely many roots. So it must be that this is not actually a true cubic polynomial. This must be the 0 cubic polynomial. right? So this implies that actually A0 equals A1 equals A2 equals A3 equals 0. Otherwise, we wouldn't be able to get more than 3 roots. Okay, so somehow linearly independent means not redundant, right? We sort of need all of these polynomials. If we got rid of any of the polynomials, then we would not be able to get all the polynomials as linear combinations as before. Okay, so first proposition about linear dependence or linear independence. A subset V1 up through Vn, V is linearly independent if and only if none of the vectors is a linear combination of the others. Okay, so this says that a set of vectors is linearly independent if and only if there's not any vector in there that you can write as a linear combination of the others. Right? This sort of says that you need every vector. Because if you could write a vector as a linear combination of the others, then when you took their span, you wouldn't need that vector that's a linear combination of the rest because you already have it in the span of the rest of the vectors. Right? So this is, again, agreeing with this intuition that linear independence should mean there's no redundancy in our set of vectors. I actually need all of the vectors. It's linearly independent if and only if none of them is contained in the span of the others. Okay, so let's prove this. This is an if and only if, so there's 2 directions. And I'll prove both directions by the contrapositive. Okay, so what is this direction? This direction is if the set is linearly independent, then none of the vectors is a linear combination of the others. Let me prove the contrapositive, which is if one of the vectors is a linear combination of the others, the set is not linearly independent. Right, so we prove the contrapositive. So suppose, and here, without loss of generality, let's suppose that the first vector is a linear combination of the rest. So suppose without loss of generality that V1 is a linear combination of V2 up through Vn. Well, what does that mean? That means there exist scalars A2 up through An and F such that V1 equals A2 V2 plus An Bn. Okay, now I'm looking for I'm looking to show that the set V1 through Vn is linearly dependent. So I'm looking for a non-trivial linear combination of the vectors which equals 0. How can I do that? Well, I could just subtract, say, the left side from both sides. Right? So this would mean that 0 is equal to -1 times V1 plus A2 V2 up through An Bn. Okay, but here I've taken a linear combination and I've gotten 0. And this coefficient is -1, which means that this is not a trivial linear combination. So I found a non-trivial linear combination which equals 0. So by definition, this means that this set is linearly dependent, which is the contrapositive of the forward direction. Okay, sort of a similar proof for the converse. Let's again prove the contrapositive. Right, so the contrapositive of the converse, the contrapositive of the converse is if the subset is linearly dependent, then one of the vectors is a linear combination of the others. Right, so for the contrapositive of the converse, we can suppose that V1 through Vn is linearly dependent. What does it mean to be linearly dependent? It means there's a non-trivial linear combination which equals 0. So then there exists scalars A1 through AF through An and F, not all 0, such that 0, I just lost my pen. Oh my gosh. Sorry. So 0 equals a1 v1 up through an vn. Okay, so what we know is that not all of these scalars are 0. At least one of them is non-zero. Okay, so without loss of generality, suppose that a1 is non-zero. Okay, if one of the other ones is non-zero, we could just rename the vectors and call that the first one. Well, since a1 is non-zero, it means I can divide by a1, because I can divide by any non-zero scalar in F. So then v1 equals negative a2 over a1 v2 minus a3 over a1 v3 minus an over a1 vn. Right? All I've done is I've subtracted over a1 v1 to the other side, and I've divided by it because it's non-zero. But this shows that v1 is a linear combination of the rest of the vectors. So one of the vectors is a linear combination of the others. So I've proved the contrapositive of the converse, therefore I've proved both directions. Okay. So this proposition is a nice one. Somehow it captures the intuition that to be linearly independent means something about the vectors aren't redundant. Okay, but actually we can say even a bit stronger of a result. Okay, so I've sort of broken up into two results because I think this result on its own is sort of one nice thing to think about. But your book proves this just in one go, a slightly stronger statement, which in your book is called the linear dependence lemma. So we've already sort of proved the first half. Let me just state it. So suppose that v1 up through vn, I've switched to m's. Okay, is a linearly dependent list in V. Okay, so by the proposition we just proved, this means that one of the vectors is a linear combination of the others, right? But this theorem, this lemma, says something a little bit stronger. Okay, so then there exists some j between 1 and m such that the following hold. Say 1 is that vj is in the span of v1 up through vj minus 1. And 2, if vj is removed, the span of the remaining list equals the span of the original list. Okay, so let me just explain why this is a little bit stronger than the thing we just proved. Okay, so the thing that we just proved is that if you're linearly dependent, then one of the vectors is a linear combination of all of the rest, right? Which would say that there exists a vj that's in the span of all of the rest of the vectors. This is a little bit stronger because it's saying that you can even find a vj that's in the span of just the ones that came before it, right? That's in the span of v1 through vj minus 1, not the span of all of them, but there's some vj you can find that's in the span of all of the ones before it, which seems a little bit stronger. And then also, this is saying that if you remove the vj, you haven't changed the span. So if you have a linearly dependent list, you can always find a vector to remove without affecting the span. Okay, so for part 1, we've essentially already proved it. One. So if the set is linearly dependent, right, let me just tell you how to adjust the proof. So if linearly dependent, then you can write a1 b1 plus an bn equals 0. And right, so these scalars are not all 0. Oh, gosh, m. What you do is you just take the largest thing that's non-zero, right? So you just pick, you go as far right as possible where you have a non-zero coefficient. So pick the furthest right non-zero coefficient, right? So maybe like am is 0, but am minus 1 isn't 0. And you just move it over to the other side and you divide by it, right? Because then it'll be in the span of all the ones before it, because for all the ones after it, the coefficient was 0 anyway. Okay, so in the previous proof without loss of generality, I assumed that the non-zero coefficient was a1. To prove this result, you just pick the largest, the furthest right non-zero coefficient, and you just do the same proof, and it will be in the span of all the ones before it. Okay, so that will essentially prove the first part. Yeah, I still need to prove the second claim, which is once you remove this vector, which is a linear combination of the others, that you don't affect the span. Okay, so we need to prove that a linear combination of v1 through vm can be written as a linear combination without vj. Right, so to say that the span is unaffected means that if you take a linear combination of the smaller set of vectors, every linear combination of all the vectors you can write as a linear combination without vj. That's what you would need to prove to show that the spans are the same. Right, so let's suppose that you have some vector which is just any old linear combination of these vectors. Right, so this is in the span. Right, so suppose that you have any linear combination you want. I want to prove that you can write this linear combination without the vj. Okay, but by the first part, we know that vj is in the span of v1 up through vj minus 1. So what you can do is you can take this vector, and you can write this vector as some linear combination of the first j minus 1 of them. That's by part 1. Right? Then what you do is you take these vectors plus this vector times aj times this vector, plus these vectors, right? And that is the same sum, right? You just replace vj with the linear combination of v1 through vj minus 1. And now you've written it as a sum of vectors, as a linear combination of the vectors v1 up through vm, but you haven't used vj, right? So in the end, I guess what you'll get is you'll get a1 plus ajb1 times v1 plus a2 plus ajb2 times v2 plus up through aj minus 1 plus aj bj minus 1 bj minus 1, and then just the remainder of the list. Right, I've just rewritten here what I circled in blue. And this thing now is a linear combination of all the v's other than vj. So this is in the span of v1 up through vj minus 1, vj plus 1, up through vm. So every single vector in the span of all m of them, you can write in the span of all of them other than vj, which means that you haven't affected the span. The span of these two sets of vectors is the same, which is what we wanted to prove. Okay, so this linear dependence lemma, which is, I guess, the last result that we have time for in this lecture, so I'll continue talking about this section in the next lecture, has the flavor of, a mathematician would call this kind of a technical lemma. Okay, so somehow this second statement is the kind of statement that you can maybe use to prove something else. You can use the second part of the lemma as a technique, right? I don't think it's like a extremely clean, like it's not a very beautiful mathematical statement, but it's one that we can use often, right? So in some other proof, if we get to the point where we have a linearly dependent list, what we can say is, oh, we'll just pull out one of the vectors, get a shorter list, and it has the same span. It seems reasonable that we could expect to use it in another result, which is why it's proved in the text. So I guess the first two propositions I'll start with on Monday, or virtual Monday, whatever you want to call it, will be results that use this technical lemma. Okay, so I would say this previous result is sort of the more, like the pure, more beautiful mathematical statement. Set of vectors is linearly independent if and only if none of the vectors is a linear combination of the others. Right? It has like just a clarity to it. This result is more specific, right? It's more technical. We'll use the result, but sometimes you want to have results like this in order to prove other things. So that's why we prove this kind of result, just in the service of proving other things. All right, so I will see you next time. How do I stop the recording?